the next, so our model for the op amp so far is now we have so this is the ideal op amp. We have already talked about the saturation limits and okay. Now, so far we have assumed that the output of the op amp is an ideal voltage source. It is a voltage controlled voltage source with a very large gain, and by definition a voltage source is one where the output impedance of the source of an, what is the output impedance of an ideal voltage source? 0, right. So, so we so far assumed that the output impedance of the op amp is actually 0, but please bear in mind that nothing in the world which is supposed to be 0 will be 0, and nothing in the world that is supposed to be infinite will be infinite, right. So, in reality what happens is that every op amp will also have some finite output resistance R O. Okay. That will be small, but again small is a relative term, right. So, it will, I mean you will have to look up the data sheet of the op amp to basically look at what it actually is. And so, now so what does this mean therefore? If you have an op amp with finite output resistance, what comment can we make about the output resistance of amplifiers we use? We take the op amp and build an amplifier, isn't it? So, what comment can we, I mean before we actually do the analysis, what do we think, what should we expect when we take this op amp and put it inside a feedback loop? Earlier we said that the output resistance of say a voltage controlled voltage source or the inverting amplifier or the non-inverting amplifier, the output resistance was 0, correct. That was assuming that the op amp behaved like a voltage controlled voltage source. Unfortunately, it does not. So, what do we expect the output, what do we expect now to happen to the amplifiers that we have built? Yeah. So, basically the output impedance we should expect that it is not 0 anymore, right. So, let us actually do some calculations and figure it out. So, so let us assume that we have, again let us go back to our input, let us assume for the time being that the when we deal with this non-ideality, right, let us basically so let us say this is actually let us just use an ideal op amp and then put a resistance in series with it. So, we assume offset is 0, okay. But now we have a resistance R O in series with it. So, let us assume that A is so large that I mean let us assume some finite A. So, what do we do? I mean so let this is V O. If that is V O, what is this voltage? What is that? What is that? Very good. This is V O by m plus 1. So, V in minus V O by m plus 1 times A represents what voltage? all right. So, what does that represent? See, the op amp is actually this thing, this whole thing here. Okay, it's an ideal op amp with a resistance of RO in series with the out. Does it make sense? So, what does V in minus VO by m plus 1 times A, what does it represent? Yeah, it basically represents the voltage at that node, correct. So, this times m plus 1 R, notice that these three form a series connection. So, m plus 1 R divided by R naught plus m plus 1 R must be V. All right. So, how do we, so what happens, so how do we do this? So, basically we take all V in times A times m plus 1 R by R naught plus m plus 1 R must be equal to V O times 1 plus A times m plus 1 R by m plus 1 times R O plus m plus 1 times R. So, this goes away. So, what do we have? V O by V in is A times m plus 1 R divided by R O plus m plus 1 R divided by 1 plus A R by R O plus m plus 1 times R. Yes? Is there a mistake? No, that is okay, but is this correct so far? Okay. All right. So, basically this is nothing but A times m plus 1 times R divided by R naught plus m plus 1 times R plus A times R. Sanity check as A tends to infinity, it is m plus 1. So, basically we can write this as m plus 1 times what was there on the numerator, AR. So, we divide by AR and this becomes AR, correct. Okay. So, sanity check as A tends to infinity, even if there is if A is infinite, VO by Vn is still equal to m plus 1 even with finite or not. Does that make sense? Okay. If it is not, when if A is not infinite, then what comment can we make, which is basically this is m plus 1 divided by, let me write this in this form, 1 plus r naught plus m plus 1 times r by A times r. And let us try to relate this to a formula we already know. In a negative feedback system, what is the closed loop gain? In a negative feedback system, the closed loop gain is is 1 over the feedback factor times loop gain by 1 plus loop gain, where loop gain is A times F, correct. Okay. So, basically which is the same as 1 over the feedback factor times 1 over 1 plus 1 over loop gain. Okay. And what is so now staring at the two expressions, what is the loop gain? Loop gain is nothing but AR by R plus MR plus R naught. Okay. And basically it is like we broke the loop here, yanked this side up and saw what came back. What if this goes up by some delta V, this goes up by, if that is delta V, what is that voltage? Delta V, look carefully and answer. R by M plus R plus R naught. Okay. And so what is the voltage that comes back there? Yeah. So basically it's minus AR delta V divided by M plus 1 R plus R. So there is negative feedback, and the ratio of what you put in to what you get back is AR by M plus 1 R plus R naught. So the loop gain is it indeed turns out that. Does it make sense? All right. So if the gain is very large, then so with R was, when R was 0, the loop gain was, what would the loop gain be? Pardon? A by M plus 1, right? If R0 was 0, what would be the loop gain? R naught. A by 1 plus M, right? Now that the loop gain has changed to R by R plus MR plus R naught. Okay. So, so if R naught is small compared to R, correct, what comment can we make about the loop gain? I mean, if R naught is small compared to R, the loop gain is virtually not changed. It was very large earlier, now also it is large. So, the what cause, so that therefore, the closed loop gain is still going to be, what is the closed loop gain? Closed loop gain m plus 1, all right. Okay. So, the loop gain has not changed very much because of R naught, and therefore, the closed loop gain remains m plus 1. Now, what if you deliberately make, I mean, if you choose this R, the resistance very badly, and therefore, you let us say the R you put in is smaller than R naught, then what comment can you make? The loop gain will become smaller, much smaller than what it's supposed to be. Does it make sense? Okay. So, if this R naught, if this R is chosen to be comparable or smaller to R naught, then clearly the denominator will become will not remain the same, right, and therefore, you basically will end up with a loop gain which reduces. So, therefore, as far as the if you look at okay. All right. So, the as far as this circuit is concerned, the Thevenin voltage is what we have just found out. That's the open circuit voltage, right. Now, we need to find the output resistance. What do we need to do? Yeah, we need to find the Thevenin resistance. So, basically, to find the Thevenin resistance, we do the familiar thing of applying you set the independent voltage source. Which is the independent voltage source here? Vn. We set Vn to 0. And then we apply we test and find I test. Let me call that Ix. So, the output resistance capital R out is nothing but V test by Ix. All right. So, what is this? What is the voltage at this terminal? V test by m plus 1. That voltage therefore is minus A V test by m plus 1. Okay. And therefore, what will be that voltage? What will be the current? What is the voltage across R naught? V test minus minus of this thing, that is A times A over m plus 1 times V test times 1 over R naught is I x. This plus, what is I x? So, there is 2 parts to I x, one is that part, and what is that current? Yeah, V test by m plus 1 times R. Okay. So, that is basically V test by m plus 1 times R. Okay. So, let us so V test times 1 by R naught plus A by m plus 1 times R naught plus 1 by m plus 1 times R is I x. Right. So, therefore, I x by V test, that is the output conductance, is the sum of 3 conductances. So, how can we model all these 3? Some inverse of resistance is what conductance means, right. So, if you want to draw a circuit diagram to represent this, what will you do? 3 resistors in parallel, and what are the resistors? What are the 3 resistors that you will put in parallel? R naught parallel m plus 1 times R in parallel with m plus 1 times R naught by A. All right. And of these, which will be the dominant, which will dominate? So, V test by I x, therefore, which is approximately equal to, if you have 3 resistors in parallel, the smallest resistance is basically thing, and since A naught, since A is a very large number, right, m plus 1 times R naught by A will definitely be much smaller than R naught. So, you basically will find that this is m plus 1 times R naught by A in parallel with m plus 1 times R. Okay. And if R is if R is say larger than R naught, then the output resistance R out is approximately the output resistance of the op amp divided by A by m plus 1. And what is A by m plus 1? Is the, what is A by m plus 1? I mean, what does that indicate? It is the loop gain, right, when it is, I mean, or rather it is approximately equal to the loop gain when R is small compared to capital R and m plus 1 times R. This is the approximate value for the loop gain. So, what do we conclude? The Thevenin equivalent of the amplifier is basically we have V in. So, we have its equivalent to R out is approximately and the voltage is approximately m plus 1 times V I times 1 by 1 plus 1 by loop gain, and that's A R by m plus 1 times R plus R. Okay. So, if A is very large, this is approximately equal to m plus 1 times V I, and the output resistance. The key point is that the output resistance of the op amp in the presence of feedback, right, or rather the output resistance of the closed loop amplifier is the output resistance of the open loop amplifier divided by the loop gain, right. So, closed loop output resistance is open loop output resistance divided by the loop, right. Okay, there are some approximations involved because it's not really, the output resistance is not really A naught R naught by A by m plus 1. There are some other terms, but loosely speaking, this is what it is. All right. So, for every time you see the op amp enclosed inside a negative feedback loop, you will find some relation of this form, right. So, the output resistance of the op amp when enclosed inside the feedback loop, when you look into the output terminal of the op amp, the output resistance is reduced by the factor of the loop gain.